Now that consists about 8 slides, and then the second part, the grid of the future challenges. Okay, I named that section in my slides as a wind of change, because that is the wind that is blowing the change onto the industry. So we will look at things that are forcing the power system to change and understand what these changes entail. This is where I will spend a lot of my of the session looking at the certain aspects of energy transition. Finally, the last 4 part is a bit of propaganda by TNB, which tells you basically what we are doing in making that shift, in enabling the energy transition. So there will be only 4 slides. Okay, now let's start from this. This is our current power system. I've simplified it a lot. Okay, I hope you appreciate that, and I hope there's not too many power system experts in the audience, because then you will find out that I'm really simplifying things. Okay, this is what we have right now. Starting from the left, we have the generation. This diagram is quite easy. Everything flows from left to right. Okay, so we start with generation. What we do there is just converting one form of energy into another. So basically, burning coal, okay, and then to turn the rotor, and then to generate electricity. It's just converting one form of energy to another. Now, we have what? Hang on a second. Give me a second. Okay. Sorry. I think. Okay, never mind. Sorry. So currently, the small box at this bottom. Can you see my cursor, Azik? Or do I need to put in the presenter thing?
Yes, I can see.
Okay, let me do the. Okay. Right. So this is not the total generation in Malaysia, in West Malaysia. This is only for TNB. Okay, for generation, it's basically a competitive market. We have IPPs, and we also have a TNB. Okay, for your information, TNB is a vertically integrated utility. So that means we've got generation, transmission, distribution, and retail. Okay, so system is quite simple. We burn fuel to generate electricity. So converting one form of energy to another. We transmit the electricity through our transmission network. Okay, we have got, okay, let's go back to generation first. We have got, for TNB alone, we have got about 14,000 megawatts of capacity. Renewables is about 1.82%. Oil is 1.47%. Hydro is about 18, coal 30, and gas is 47. So you can see hydrocarbons form a majority, about over 75% of our generation capacity. Okay. Now, so the system. Okay. So power is generated. Sorry. That's embarrassing. I had to throw out my cat. Right. Fine. Okay. So essentially, yeah, okay, our transmission network, we have got about 666,000 circuit kilometers of transmission distribution line. So we transmit at, on our transmission voltages are 500 kV, 275 kV, and 132 kV, 102,000 volts. On so we have about, in total, about 80,000 transmission and distribution substations. Okay, majority of it is distribution substations. For the grid, for the transmission network, we have, I think, about 470 substations, 170 transmission substations. Now, inside our system, we have got about 92,000 over transmission and distribution transformers. Okay, so basically, we generate electricity. The generators will pump out power at a voltage of about 11 kV or or possibly 33 kV. So it's low voltage. So we have step up transformers that steps it up either to 500, 275 or 132. Typically it's either 500, 275 nowadays. Okay. 132 kV transmission is on the older generation. And we transmit it all over Malaysia, West Malaysia, okay, until we reach by stepping down, and then we step down the voltages to the distribution levels. Distribution level voltages is 33 kV, 11 kV, and finally to the substation in your housing area, it will be about 415 kV, 415 volts. Okay. Now, so and then of course we have the customers who forms the load and the commercial load. We have about 9 million over customers. Okay, TNB has got 9 over million customers. Now, besides the figures, which is actually just data, what I want to stress is that in terms of, okay, so this is what we do, okay? This is our day-to-day job in TNB, in whoever is involved in the electrical supply industry. So on the generation side, we have many forms of energy sources. Currently, hydro, gas, and coal being the predominant ones. Okay, but like I showed you before, we have got also some renewables. So in terms of energy source, we have flexibility. Okay, and then our job is actually to balance supply and demand. Okay, what we have in the system is actually a collection of machines rotating at the same speed, synchronously through a magnetic field to generate electricity, which is sent to the load to do something useful. Okay, managing and operating the electric power system is like running an instantaneous on-demand service 24/7. Every time somebody turns on the switch, we are expected to deliver the electricity. Okay, when they switch it off, we need to, well, I won't say take back the electricity, but basically stop producing the electricity. Okay, so ours is a business of trying to balance supply, which is the generation, and the demand, which we call the load. Okay, now it is also about managing and balancing the reactive power and active power. Okay, active power is actually the megawatts, reactive power is actually the megavar. Okay, the useful energy is actually the active power. That is where we bill you for using. Okay, that's what drives machines and stuff like that. But the system requires reactive power. Okay, primarily to provide the magnetic field for the generators. Otherwise, they can't produce electricity. So basically, it's also to produce the voltage that they will drive the current. Okay, so on the left is the generation. We are balancing the supply and the demand. What do we look at to balance the system? We look at to balance the load. That means to make sure that the supply meets the demand, we actually look at the frequency. Okay, and to manage the reactive power so that we can maintain the power flow in the network, we look at the voltage. Okay, now besides that, we have to contend with losses, we have to contend with failures, and we have to make sure that we don't transgress the physical limitation of the grid. Okay, we are not supposed to transgress to exceed the physical limitation, but to make it cost effective, we need to run the system to its most optimum capacity. Okay, so we will revisit this diagram again, but our generation, the driver is that we need to produce energy with the least cost. Number one, we need to make sure that there is sufficient generation capacity to meet whatever demand on that day at that particular moment. Okay, on the transmission and the distribution network, we need to make sure that we have the capacity to transmit, to distribute the power, to transmit and distribute power. We must make sure that the network is reliable. Okay, so that there is no interruptions. All that is just to make sure that we provide accessible, affordable, reliable electricity supply. That means we are making sure that we keep your lights on. Now, on the demand side, I will show it to you a bit bigger, but the demand is variable because people use electricity different times of the day, switch things on, and then that's why it's variable. So this is the load curve, the system generation megawatt. Okay. Now we will revisit the electricity. On top of that, we need to make sure that in case anything happens, if there's a disruption or fault, we need to be able to recover the lost generation. Okay. All right. So um, the first I mentioned just now, we're doing balancing, and then we're looking at frequency as well as voltage. So it's like driving a car. You need to look at your speed. I think that's all you do. Okay. So when we drive the power system, we look at the frequency and the voltage. Okay. Frequency, we are looking at it to make sure that the supply matches the demand. And then the voltage, we look at it to make sure that there's enough VARs in the system to drive power flow. So I want to introduce the concept of system inertia. Okay, this will become important later. Now, I put up a simple heat engine here. Okay, just to show how basically we convert one form of energy into another. So basically, we use typically a dense form of energy, such that coal, gas, and stuff like that. We burn it, we heat water, and then the water creates steam. Steam pushes piston and a wheel. Okay. Now you take this wheel as if it's inside the electrical system, it'll be a rotor rotating inside a electric field to generate electricity. Okay. So right. I want to introduce you the concept of system inertia by looking into, on your right hand side, the frequency response. Okay. Now when we have a disturbance, okay, when we have a fault, okay, typically when we have a fault, I give you an example. If our line if our line snaps, if our transmission line snaps, drops down to the ground, what we'll have is actually part of the system being earth. Okay. Now when you have a system being earth, you have a fault current going through. That means the system will draw for a period of time a lot of current. So then typically, because of that load, the fault current load, it will slow down the engine, the heat engine. Our rotating machines will just slow down because of the extra load. Okay. So we have systems in place to clear a fault. So it means sectionalize the areas and stuff like that. So after that, the system will recover back. Now, what we have in our system is a collection of rotating machines. Okay, so we have, and all these rotating machines are rotating at the same speed. Okay, so basically at the same frequency, generating the same electricity of the same frequency, about 50 hertz. Now, once a generator loses connection with the load, okay, that means it doesn't have any load, it will spin faster. It's like riding a bicycle and then your bicycle chain snaps. Okay, then you will do that the overcycling part. Okay. Similarly, when the load goes up, that means when you have extra load, the machine slows down. You have to cycle harder. So that is what I mean. Inertia is just this. Give me a formal. The formal definition is that resistance to change. So something which is moving tends to keep on moving. So in our case, when we have inertia, means the machine will still be rolling and be generating some energy. There will still be energy. So it's important for a power system to have this inertia. I hope I make that clear. But we can revisit again. So who are the players in the Malaysian power system? Okay. Now TNB is not the only one who decides on generation of electricity. In fact, TNB Tenaga Nasional plays quite a limited role. Okay, so the single buyer and the grid system operator plays a key role. The single buyer actually buys electricity. They will manage the contracts. They will buy the electricity, they will do the fuel planning, and they will prepare the medium and short-term capacity scheduling. Okay, so basically it's a plan that says, okay, we're going to, these plants will be operating and stuff like that, and so they will pass it to the grid system operator. Grid system operator is responsible for the day-to-day real-time operation. Okay, and the management of the peninsular grid system and the interconnections with Thailand and Singapore. Okay, so TNB is essentially just we own the assets, and then if we are responsible to put up more assets as well as to maintain the national grid and the distribution network. Okay, so we have no say in the dispatch of energy, which plants operate, which plants don't operate. Okay, and we don't actually control the electricity flow. That is done by the grid system operator. So the key player in this is the grid system operator. Now I'm just showing you what happens on a weekly and a day-to-day basis. It's the same graph as just now, which is the challenge of matching the supply to the demand. Now the grid system operators will typically have the week ahead demand forecast. Okay, so and then the week ahead generation mix. So they have that as a plan, and then on the day of on the day they will start dispatching and scheduling the generation to match. That's what they do. Because load changes fairly fast, and there's a variable element to it. The system has a system called automatic generation control. Okay, that matches in real time the demand and the supply to the demand. Okay. What it does is it monitors the frequency and then tries to, using set points of the generation, to adjust the speed of the generators. Okay. Now let's recap. Just a quick recap. So essentially, we use dense primary energy sources. Now, you will see why I use the word dense, because when you move in energy transition, you're moving towards less dense primary energy sources. So when I say dense, it means the joules per kilogram. Yeah, the joules per cubic meter is higher. Okay, so we're using hydrocarbons, like coal and stuff like that, considered dense primary energy sources for generation of electricity. Now, our plants typically on a day, the dispatch of energy can be considered deterministic. That means if I have got 10 plants, I'm reasonably confident that they can provide me the energy I require for that day. Okay, so it's dependable. So power station A, I know, will generate 750 megawatts between certain time to certain time. Now, barring any mishaps, I am quite confident that they can provide it. Okay? Now, additionally, but I don't. Okay, so and then we have big power plants because of economy of scale as well as better efficiency. Our biggest plant is about units are about 1,000 megawatt. Okay, so those are the coal plants in Jima, in Manjung, in Tanjung Bin. So and they are our cheapest plants as well. Okay, so we've got big power plants because of economies of scale, and it's cheap, well, cheapish. Now, we have a long planning cycle. Okay, it takes when we have got for our transmission, we've got a 10-year plan because it takes realistically about 8 years to build a transmission line. Okay, and then it takes years as well from the planning up to the final thing to build a power station. So we have got a long planning cycle, and essentially for the last 30 years, we can always expect demand to grow, load to grow. So it's a matter of just planting up. So admittedly, I think about 30% for our installed capacity reserve is a bit on the high side. Okay, so and then let me see what else. All this costs a lot of money. It's high capital investment. Okay, and the others is operational. It's one-way power flow and so on. What I'm trying to get here now is that we have sunk in a lot of money in the electric power infrastructure. Okay, now when we're talking about energy transition, which is the primary topic for the day, you want to change that system, but you must be mindful of the investment that you've already done. Okay, you cannot strip everything and then start new. So that is why we need to understand that we need to work with the system that we have. Now, currently it's one-way power flow. Later I'll show you that with RE and distributed generation, the power flow will not be one-way anymore. And that forms a problem because our system was planned and designed to be one-way. Okay, and now that we have got injection on the load side, it does create some issues. Okay, now in terms of operation, it's a balancing act to make sure that the supply matches the demand. We need to make sure that there's enough reactive power and active power, and we do that by looking at voltage and frequency, maintaining the voltage and frequency within the limits. So that's how we maintain the system stability. Of course, we are doing all this to make sure that electricity is affordable to you. Okay, let's go to our next. Okay, this one, I apologize. I've got two versions of this. This is the gangster version. Okay, on what is driving energy transition. This is the more politically correct version. Okay, so since I don't actually get any feedback from you, I want to go with the gangster version. So why are we pushing for energy transition? This is my take, completely my take, my opinion. We need to go for energy transition because we do not want to die. And we are going to die because we are messing up the weather and we are changing the climate. How do we do that? What we are doing now is that we are emitting a lot of greenhouse gases, in particular carbon dioxide, and that is trapping the heat from the sun on our earth. So if you read, I think you're students of RE and energy transition, and you should know that we are trying to target to stop the world temperature from increasing by more than 2 degrees. The 2 degrees is our limit. Okay, now because if we pass that 2 degree limit, the world will change. So I think I will mention it again later, but the climate change, the race against climate change, the way that we are trying to use renewable energy, we're trying to harness energy from the sun, from the wind, from the waves, we are basing it on one fact. We are trying to harness the power of nature when nature looks like it is today. But climate change is going to change nature. Okay, so instead of nice breezes or wind power, we may have hurricanes. Okay, so there will be a tipping point with climate change that whatever investment that you put up to build up RE, if you don't do it fast enough, will just will just go to waste. It's a tipping point. At the same time, we are destroying the environment. Okay, we are making species extinct and we are poisoning the environment that we live in. Now, so that's why sustainable. I've got an issue about being sustainable and green. Okay, so I think there are slight differences to that. You can be sustainable. You can have sustainable energy, and this may be controversial, but you can have sustainable energy by using nuclear. Okay, nuclear is clean. It doesn't generate carbon dioxide, so it's a clean form of energy. However, once we have it creates other issues, but in a way, there's ample resource, right? There's ample, and then if nuclear fission comes through, the holy grail of energy comes through, then we will have really abundant resources. So one, climate change, we're going to die because climate is going to change. We're going to destroy the environment. That's why we're going to die. We're going to run out of resources. There's just too many of us, and the resources are not divided equally. Okay, and the fear of scarcity influences behavior, and that started 100 years ago. We fight wars because of the greed for resources, trying to control resources. Okay, finally, anarchy. This is what I mean by anarchy. The society will disintegrate into anarchy. We will kill each other. We will have unrest. Why? Because there's a gap between the have and the have-nots, and we're creating an entitled society. We're also coming up with a disenfranchised society. Now, you see a frog down there because there is this story about how do you boil a frog. So essentially, if you put a frog inside water and then you turn the temperature slowly, the frog will not jump out and it will eventually die. I think that's what's happening to the world, to us. So if you don't pay attention, we will end up like the boiled frog. So what can we do? Not everything is not hopeless. There is still hope. So number one, we need to stop climate change. And this is a race. I'm telling you, it's a race. We need to stop it before it tips over. We need to preserve the environment. We need to ensure sustainability of resources. And finally, democratization. Okay, we need to make sure that everybody has we have to have an equitable society where people have access to power. If you're talking about power, but I think in everything else as well. And we have to have an empowered society. So going to the right boxes, so keep the we in the power supply industry, that means me and then and you, because you're studying renewable energy and distributed generation. We need to make sure that we use clean, sustainable, and affordable energy sources. We need to make sure that we are carbon neutral in whatever we do. Okay. Now, if you read up, there are issues with even with RE on these things. We need to reduce waste. Yeah? So essentially energy efficiency. We need to be environmentally responsible. And we need to democratize electrical energy. That means make it available. Democratization of electrical energy to us is actually empowering the customer. Okay, you empower the customer up to the point that if they don't want, in case of TNB, if they don't want our electricity, we should help them get off the grid. Yeah, it's a bit controversial, but then again, remember the disclaimer right from the very start. I'm not responsible for all of this. So this is the politically correct version. Energy trilemma. The World Economic Forum and I think the World Energy Group came up with this energy trilemma. They have actually got an index for this, where they measure a country's capability of providing energy security, energy equity, and environmental sustainability. Okay, so Malaysia has committed in terms of the greenhouse gas to reduce the emission intensity by 45% by 2030. And then there's some caveats there. And we hope to achieve 31% RE capacity mix by 2025. That is in 4 years' time. Okay. Now the drivers for energy transition just now I gave you my version of the drivers, but it is basically the same. Number one is decarbonization. It is about reducing CO2. Decentralization is about generation being in smaller pockets. So that's decentralization. Democratization, I've already explained. And democratization is also referred to as deregulation sometimes, or most of the time. Okay, but I took it one step further and put it to the extreme and call it democratization. Deregulation is just removing the regulations, loosening the market, but with the aim of some degree empowering the customers. Okay. So digitization actually, the three are things that we need to do. The four is actually an enabler. The digitization is helping us to achieve what we want. If we can play it, we can do it right. Now, in short, I think I got this off the internet. So you probably will see it. So our power generation structure will move from a big, large fossil fuel power plants to many smaller renewable energy generators. Market currently is sort of centralized. It will be is moving towards decentralization. It's not happening too much in Malaysia yet. But I think there will be strong drive for it. Okay. Because of the transmission network, it will change primarily because the power flow has changed, so we need to manage that. Distribution now in the current days, well, not in the current days, but we used to have a single direction of power flow. Now we're going to have multiple injections on the distribution end. Okay, we will explore all this the reason. Measuring units, now we've got smart meters, and from consumers we're going to have prosumers, customers who actually at one point in time will sell electricity to the grid. Okay. Now this is from that energy trilemma, you can translate it to the power utility trilemma. Okay. Last time you only had trilemma, which is we have to make sure it's reliable, we have to make sure it's affordable, doesn't cost too much. Now we have another thing to consider, which is sustainability. So that's why it's called trilemma. So with affordability, we need to improve energy efficiency. We need to maximize flow in constrained and aging grid. Okay, our grid is about let me see, about average age is about 25 years old. So we're getting, most of our assets are getting old. It's also about connecting DERs to an energy system, leverage information across the supply chain. Then the thing that we need to ensure, like we always have ensured, is reliability. The new thing for us will be about sustainability. Okay, new, when I say new, is a new for us since the last 10 years. Okay. Oops. Oh, sorry. Okay. So this is the outlook on for the future generation sources. Okay. This changes sometimes, so I'm not sure when I got this, but we aspire to have about 1.2 gigawatt of renewable energy by 2020 and 4 gigawatt by 2025. Now the 4 gigawatt in projection is based on large scale solar. Large scale solar is anything above between 30 to 50 megawatts, okay, of solar. So they're typically either connected on the transmission grid, or for smaller than that, it'll be on the distribution grid. So we expect to get 4 gigawatts, but experiences overseas in other countries have shown that with large scale solar, you can more or less plan the plant up, because in Malaysia, we have tenders that goes out for large scale solar as tenders. Okay, So in a way, you can control and decide where to put this large scale solar, because TNB shares information about our network on where are the ideal places to connect to the network. So large scale solar is not too much of a concern because it's almost in a way predictable in terms of the capacity. However, in other countries, we have found that when you typically when you plan for 4 gigawatt of the large scale and stuff like that, you will get another 2 gigawatt or half of, or 50% more that comes from rooftops. Okay, through incentives and stuff like that. This is the normal customers. They will put up solar panels on their roof and they will start generating and contributing to the grid. Okay. Now, Malaysia is actively promoting that. We have SEDA that is rolling out programs like net energy metering and stuff like that to encourage household generation of electricity. Okay. So that is what's happening now. In case anybody asks, there's not much wind. Onshore, there's not much wind. I think offshore, I'm not too sure. There was some talk that there's wind energy from the East Coast, but there was a study done, and I think the study by one of our local universities did not find much potential there. So there is some potential in Sabah, but Sabah is called the land below the wind for a reason, because the wind doesn't blow that much over there, just below it. Okay. Right, so that's the outlook for future energy generation sources. Now let's revisit the network, our power system. So now you still have the old big generation, thermal, which you're hoping to reduce. You will have grid connected solar on the high voltage. You will also have distribution connected on the medium voltage network, directly connected network, some solars. And we don't have that many, but soon you will have electric vehicles running around, and we have the household solar. So the power flow is now going to go both ways. So there's no longer a single direction power flow. Now, what have I got? Okay, so remember I told you that this network was designed a long time ago. In fact, our network, our current electrical network, is very similar to what it looked like when the first network was built. Okay, in principally, power flows from one way. You plan for it, you design the network, you calculate the fault current, the fault levels, based on that single unidirectional power flow. Now that so when we sized up everything from the equipment on the distribution end, that is how we had planned it. Okay, so we never catered for generation coming in from the distribution end. Okay, so it does give a bit of complication. Number one, it has it brings about issue on our fault levels. Okay? Because you're changing the electrical resistance path, impedance path, and stuff like that. So there is an impact, and you will see that if you put REs due to its nature, you also will we need to change the protection system, because now energy is coming in from the demand side as well. Okay, so I have purposely not included batteries, because batteries is actually a solution. So we will be the grid will have batteries in future. Now, one interesting thing is electric vehicles. Okay, electric vehicles, they are definitely a load, because you need to charge your cars, charge your batteries. Okay, but they can also be a source. Okay, they are batteries, they store energy. So they are both a load and a source. And one more thing is that they are mobile. Okay, so if there was no COVID, come Hari Raya, everybody will be going back to their hometowns. So all this, if we had everything, we have got a lot of electric vehicles. Can you imagine all these loads moving now? So instead of having the load, it used to be in KL, now it is in Kota Bharu. Now it's going to be in Kuala Kangsar. So it's moving load. So it makes it a bit more challenging to operate with a moving load. But we don't have that many EVs to be concerned about, and we don't have that many EV charging stations to be worried about. But as you know, the government is promoting EV, so there will be a drive on that. Now, all right. So the future you'll see that there's rooftop solar. There's bound to be microgrids, people who actually run and operate their own grid and use our the traditional grid for backup. Okay. You're gonna have a lot of large solars and stuff like that. Let me see. I'm wondering whether if you see the opportunity here. Okay. Let me tell you something. The grid system operator who manages the grid, okay, the single buyer who manages the purchasing of energy, currently only in this current scenario only deals with a few players. Okay, because the power stations, we don't have thousands of power stations. We only have quite not too large account, so it's manageable. Okay, but imagine now you have got prosumers who's trying to sell electricity. You're going to have solars putting in on the medium voltage level, on high voltage level. And if you see the solar LSS contracts, we push out, I think, 20, 30 solar plants at one time. So managing all these energy suppliers is going to be a headache. So there could be a headache for both sides, both for the person buying the electricity as for the person selling the electricity. Okay. Now, if I've got 2 kilowatt of electricity, I will not have as much push or influence on the buyer as somebody who has got 2 megawatts or 20 megawatts. So there is a role for an aggregator here. Okay. Broker. So the entrepreneurs among you might want to explore a bit further on this opportunity. Okay, I won't share too much on that. Now, I've mentioned that the grid of the future, I think the grid of the future, especially the problems are actually already here, most of it. But the grid of the future will be more complex with bidirectional power flows. In terms of generation sources, your large scale solar, the thing that we have to be concerned about is intermittency and variability. Okay, the loss of inertia. Okay, if you look, these charts that you see here are real charts. It means we have put in our sensors in solar plants, and this is what happens on generation. I've got a better picture later. But look at the intermittency and the variability. The intermittency, you can see the supply going down to zero. Okay, so and then this is on a clear sky day. The radiation profile on a clear sky day. This is a radiation profile when there's rain, and then this is with clouds. Okay? So this intermittency and variability is the one that is causing a bit of a problem. There are ways to handle it. So then the other problem is about loss of inertia. Okay, our PV plants are essentially static. They don't move. They don't have any moving parts. So basically, they don't have any inertia at all. Okay, so the loss of inertia is a concern because it doesn't. When we have a fault in the system, PV plants, if they don't have initial control or initial help, they will facilitate actually the collapse of the system, because once you replace a high inertia generation source with inertia with a source that has no inertia, then you are actually weakening the system. In UK, there was a blackout in UK, London. There was a blackout in London because of this. There was a fault. The system did not have enough inertia, and then it cascaded into a blackout for the London region. Now, interestingly, the London, the National Grid at the time, I think, or the utility there, was actually piloting inertia, measurement of inertia, system inertia. Okay. So you might want to look into that as well. It's quite interesting how we measure inertia. Because if we know the inertia of a system, then we know what to do to mitigate certain contingencies. So not knowing what is the inertia, the capability of the system to withstand a fault makes us blind in terms of operations. Cannot prepare for it. So another thing is that solar PV plants, traditionally it's not a dynamic voltage source. It doesn't produce any VARs. Now, why I'm hesitant to talk about it, because right now with smart inverters, you can actually introduce VAR and actually introduce inertia. So it is hopefully a problem that's going away, as long as our grid code, our distribution code mandates that any PV plant that connects to the grid at any level must have the capability to provide support in terms of fault right through and voltage support. Okay. Now, because of the change in the power flow, you change the fault level, and that means some of our existing equipment we may need to replace because it no longer can handle the fault level it was designed to, because it was never designed for injection on the distribution side. On the customer side, like I said, you're going to have people planting up their own rooftop solar. You're going to have electric vehicles, and you're going to have microgrids coming in. I did some checking a couple of years ago on how real this microgrids are, and at that one point in time, microgrids does not need to be using RE. Okay? They have micro gas turbines. You can use gas to just build your own microgrid, and with all the control systems. And then I think at that time, a few of the suppliers were actually providing financing. So, but I guess it's been a couple of years, so I don't see any much take up on that. So I'm not sure. So microgrids can also run on conventional power plants. Okay, so it doesn't actually have to be. Petronas runs their own sort of microgrid in Kuantan. They call it the CUF Kerteh. They actually run their own small microgrid. You can consider NOR in the north that's running the industrial park where Intel and everything. That is also, in a way, a small microgrid, but using conventional sources. So I think what we expect to see is a mix of both. Okay, so I've explained. Oh, I'm sorry, I think I'm almost run out of time. Aziz, am I okay for time? I'll proceed until somebody tells me.
Sorry.
I'm supposed to stop at 3:30, right? Can I continue? I'll try and rush.
Okay. Yes,
Right.
you may continue.
Give me about 10 minutes and I'll try to wrap up. Okay, so remember this balancing thing. Now, on the left hand side generation, we had flexibility. Now with solar, we're going to have variability. Okay. Now I will introduce. You see the duck. This is the famous duck curve. If you're learning about RE, you're going to be introduced to this duck. Okay. This is the impact of renewables onto the system dispatchable generation. So this is the impact because typically solar peaks in the daytime. So this lubang you see here is the hole, the dip you see here is actually how the impact of the solar onto the demand, onto this supply, dispatchable generation. So that means at this time we need to tune down our conventional power plants. Okay, on the right hand side. Okay, so basically everything else is still the same. We need to do this. Okay, now instead of just making sure the lights are on, we need to, instead of just affordability and reliability, we now need to make sure it's sustainable. We have to be green. Now on the load side, okay, we used to have variability. That means supply will have to match the demand. We need to also consider if demand can match supply because of this variability. Okay, so that means we need to try to flatten out. So basically we need to try and flatten out the generation, so we don't have the peaks and stuff like that. Okay, so implement flexibility at the demand side, we need to not only look at technology, but we need to look at policies and actually market. We need to introduce time of use tariffs. We need to restructure the whole tariff. Okay, we need to incentivize people. Now, in terms of incentivizing the demand to match the supply rather than supply match demand, you need to incentivize loads, like to participate, to volunteer to switch off when there is a lack of supply. Okay, so that again is another, there is opportunity there. Right. So these are the solar PV challenges. Left hand side is about reduced dynamic VAR source. It's about being able to support voltage. Now there's an issue also with voltage, especially for the ones solar that is connected to on the distribution side. Okay, because of the intermittency of solar, that means it goes off and on, off and on. You will have disturbances on the voltage on the distribution end. Voltage is a local problem. That means it is closer to the load, whereas frequency is system problem. Okay. So power quality is an issue if you have when you introduce intermittency at the distribution end. Okay. Changing fault level, I've mentioned two things. Our major switching equipment, the primary equipment, the circuit breakers and stuff like that, our bus. It was designed for one-way power flow, and the fault levels were calculated based on that, on the impedances that stuff. Now there's bi-directional power flow. Number one, you need to change the protection. Number two, it impacts the fault level, the impedance, system impedance. Intermittency and variability, I will explore more later because I've got actual data, I think from 8th March. Loss of inertia is basically when something goes wrong in the grid, solar PV, because it doesn't have any inertia, it cannot support. Okay, the duck curve again, this time with a bigger duck curve. Okay. All right, so those are the issues with the solar. I'm sorry, I'm going to have to speed it up. Now, this is interesting. These are all the solar plants, the large scale solars that we've got. These are actual measurements that we have taken. Now, these are the from we've got 25 grid connected, and I think this is from, I can't remember, 9, yes, 9, from 9 solar plants. And this is the total for the 9. Okay. Now, if you look at this, you can see the intermittency, the variability in each of them, right? But if you gather them all, you can tend to smoothen out a bit. So having solar plants distributed everywhere around the country will tend to smoothen the intermittency and the variability. But I did a quick check, I think a couple of days ago, because I was thinking of an idea where I was looking into the virtual power plant concept of having one guy to aggregate all the supply from large scale solar. So we are banking on the fact that the sun must shine somewhere. Okay, so I was looking into that, but I actually came across a satellite photo where the whole of West Malaysia is covered with clouds. So we need to consider that West Malaysia doesn't have a big enough land size for us to leverage on location. So key issues of VRS, I summarized it at the right hand side. Now, because of the nature of unpredictability, we cannot dispatch. When I say dispatch, is schedule it put inside our schedule of generation. It is non-dispatchable. Okay, because there's some degree of unpredictability. We can run forecasts, but typically currently, I think in the most of network operators, they just take if they can get it, but then if the system cannot handle it, they will curtail. That means they will just say, I don't want any more solar. So then solar, we are wasting energy. Okay? So there's curtailment if there is an issue. Non-controllable variability is even when it is available, it will go up and down. Okay. So every time it goes down, somebody must compensate for it. Okay. Every time when the solar generation dips in for example in this I think how many minutes, how many hours within this hour, somebody, and that somebody is typically a thermal power plant, needs to pick up the pace. Okay, needs to pick up the slope because the solar just generates according to the amount of radiation that it gets. Okay, so the load is still there, the demand is still there. Somebody has to make it up. So there is an issue with spinning. I'm not sure whether I covered spinning reserves. Now, in our conventional system, when we don't have solar, the rule is that we have spinning reserve. That means machines that are synchronized to the system. That means it's rotating. Okay. The purpose, but it's not producing load or not producing its full load. So when you have a generator tripping up, or in this case, a solar leaving, not producing, this spinning reserve will take up the slack, will pick up the load. Okay, because it's already on bus and it's already spinning, it will automatically ramp up to pick up the load. So that is spinning reserve. So our rule currently is that we must have enough spinning reserve to withstand the loss of the largest unit. So our largest unit is 1000 megawatts. So theoretically, we should have a 1000 megawatt spinning reserve. Now, spinning reserve is actually a waste because you're burning fuel for something to turn for no reason. Okay. Now, we also use hydro as our reserves. So in hydro, we actually run the generator, we run it as a motor because we need to keep synchronized the system. Okay. So when we need it, we just open the floodgates, let the water, and then we convert to the generator. So there is energy cost. There is a cost to spinning reserve. And that is one of the challenges that we have been looking at into how to. in a way is location dependent. Okay, large scale solar, because of the amount of land that it takes up, tends to be in far off places. Now, then there's the issue. Sometimes large scale solars are not so green, especially if you cut trees to clear the way, to clear the land. Okay. You're also depriving. I don't know. There is an issue of land use, and also there is a carbon tax. There's a carbon penalty. There's a carbon cost. Sorry. So I've explained about reduced system in Asia, voltage regulation, because when the voltage will behave also like that, go off and on. So in the system we have equipment that actually tries to regulate the voltage within the limits, and it will has to work extra hard. Power quality because of the flickers. Inverters introduces harmonics into the system and causes heating of thing. And as mentioned, protection challenges. That's a summary of. Now let's look. Now I've got data from 8th of March. We are looking at the variability and the intermittency. Okay. Now the blue curve is the system generation, which is the system generation on the 8th of March 2021, which includes solar. Okay, so the solar at that time, the solar generation, okay, if you minus the solar generated for that day, the orange curve is the generation done by the thermal units only. Okay, so this gap in between is the energy provided by the solar. Okay, now this is when solar is very small. I think it's about 3%, 3% of the demand for that day. Now, remember our ambitions is for 20%. Okay, so essentially, as it is on a 3%, I've got to make up for this gap. If I lose solar, I got to make up for this gap. So that is not much. I think it's only about less than 400, 500. And we are relatively okay with that. If we lose all the solar, we are still okay, because we cater for the biggest unit is about 1,000. So it's cost money, but I mean, it's not too bad. But if we go up to 20%, that means solar is 20% of generating capacity. I did a simple I made a few assumptions. So basically, I'm saying that with 20%, this is what the generation without solar will be. Okay, this will be the generation. The blue one will be the generation with solar. The red one will be the generation without solar, if solar is 20%. So can you see the gap? So this will be the biggest gap at this point here. Okay, the gap is about 11.5, and the required demand is 1,600. So what's that? About 5,000 megawatts? Yeah, about 4,500 megawatts. So the system has to make up for that loss of 4,500 megawatts. So traditional way, that means you must have units that will capable of giving you that 4,500 megawatts when you need it. So that means you're burning fuel in a conventional way just to make up for this. Okay, so those are the challenges. That's why I think if you read the Age recently, and from the ministers are talking, there seem to be a slight hesitancy from the government, because they're saying that, well, maybe too much solar is not the way to go for now. So we might want to slow down a bit. Okay, and not put too much solar and then jeopardize, increase the cost of operation, as well as jeopardize the security and reliability of the system. So, but our goal is to facilitate the energy transition. That means we have to solve these problems so that we can maximize renewable energy sources as much as possible. That is the challenge of energy transition. We must make sure that we are able to maximize the use of renewable energy sources, while at the same time maintaining the reliability and affordability of the system. Okay, I hope I'm almost finishing now. With all those problems, doesn't mean that we don't have solutions. We have got many solutions. Now, on the x-axis is the types of intervention that you can do. On the y-axis is the cost that will cost you. Okay. Now, to manage this intermittency, to manage this REs, we can do something with operations. Okay. Number one, we can curtail. That means basically, if we cannot handle the power generated by solar, we just switch it off. That means, but we have to pay them. Okay. There's many ways of doing it. There's one approach is doing something with the operation. The other one is about creating a market. Okay, managing the managing market. That means the other one is doing something on the load. Okay, we do that now. Basically, we are without you knowing, if the system runs into a problem, we will check the load. That means we'll black you out to save the system. Then there's also about flexible generation. Now, series cold ramping, CT, CGT, gas ramping, and hydro ramping. So networks, we need to do something on networks. And finally, storage. When I was doing some reading about to prepare for this presentation, the options for storage is huge, and the work done. I mean, even for batteries, there's so many types of batteries, so many types. Okay, I'm not going to go too much yes because I'm running out of time. Haziq also been, I think, switching on his camera and smiling at me. So I take it that I'm supposed to be. So let's look at all the solutions. You have the solutions, now you need to match them with the problems. So these are the solutions on this axis, and these are the challenges. So for RE availability, battery energy storage systems, CVR, demand response, will tackle these problems. How you want to deploy the solutions, in what degree, is another consideration, which we'll see in the next slide. Managing frequency, you can use battery for that, you can use CBR for that, you can do demand response. Managing voltage, definitely battery. Active network management, conservation voltage reduction, demand response. So network constraints, optimal dispatch, and power quality. So you need to match some challenges can be solved by one or more of the solutions, but you have to match. You have to orchestrate and tailor it. So the other thing is that you can look into cases of, okay, this is some work that we did. Okay. Now, if we want to solve a system problem where the problem is on the system, these are the so that means is the challenges are reliability, managing frequency. Those on the right hand side are the solutions that you can deploy. Okay, so in Penang, for example, we have variability issue. We need to manage frequency. We have got a voltage problem there. We've got some network constraints, optimal dispatch. So what can we deploy? We can deploy BESS, ANM, CBR, as per this thing. So it's a suite of solutions you need to match with the problem. The nature of the problem can be localized. And that means the solution that you deploy can have an impact, a mitigation impact, both locally as well as system-wide. And who do we impact? The stakeholders. If we do this, we improve system security, optimal dispatch, we save customer money, and power. If we do something on power quality, experience for the customers. Okay, this is the propaganda part. So I'm going to. So these are the issues of RES, the issues of integration. If we want to get clean, sustainable energy, we need to build resilience by modernizing the grid. We need to incorporate agility, enhance situationalness. We need to do all these things. And TNB, the grid flexibility strategy is here. This is how we want. We need to do. What we want is grid flexibility. So the purpose of grid flexibility is to support the national energy transition agenda for clean and abundant energy. What is grid flexibility? The ability of the power system to manage the availability and stability of energy supply while maintaining the balance required for grid resiliency. So how are we going to do that? Number one, we need to modernize the grid. At the same time, we need to digitalize the grid. Okay, now both these two efforts, two programs, are not something new. It's already something that those are existing programs that we have in place anyways. It's not difficult. Grid modernization and grid digitalization will definitely um, drive grid flexibility. We create grid flexibility. Digitalization we implemented primarily for operational excellence. The Green Kingdom is actually TNB aspiration. Okay, I think we more than 30% solar or something. So enough propaganda. Moving forward, grid modernization. What does it involve? It involves interconnection within region. These are all the things that we can do. Okay, we have done interconnection. However, we need to strengthen the link. We have some form of some pilots going on the demand side management. We are looking into FACTS. Okay, of course, a new controllable load. We are looking into it. Flexible power plant control, also an area. Areas curtailment is of course always there. Storage, we are also looking into it, and electric vehicles, we are tracking the industry and seeing when we need to do something, because electric vehicles are both a support, a load, and a supply. Okay, so fine. So the key thing here for digitalization, our focus is on intelligence self-healing grid. You can put this hardware, but at the end of the day, you need smarts to coordinate all these things. Okay, so it's about orchestration. Okay, so this is another form of another thing. So this is what we're building. We are focusing on our electrical infrastructure and our intelligence infrastructure and the smart infrastructure. Grid digitalization, we are planning to orchestrate. Our primary goal is to orchestrate. That means to put solutions together and make them work together so that they provide optimal impact. Okay. Okay, thank you. Okay, my conclusions, there are problems about integrating RE, but alhamdulillah, there are solutions too. Okay, the timing, I think we are right to pursue the journey for clean and sustainable energy because the technology is available. We are at the right wave of technology advancement. Okay, particularly machine learning, artificial intelligence, because we need to be able to predict. We need to forecast. Okay, we have got relatively good buy-in from everybody. We are at the point of inflection. Okay, that means the point of change. We are at the tipping point. I foresee that there will be rapid changes and development in energy policies, energy market, and also technology. There will be a shift in the investment. Okay. There are other things that we as asset owners are worried about. We are also worried about stranded assets, because when we build the system, we expect generation on one end, distribution load on one end. So we built that pipe to be very big, okay, to cater for the future. But now that pipe may be underutilized. So we have sunk investment. We need to worry about that as well. So finally, transitioning from conventional fossil fuel energy sources to clean, sustainable energy will require taking a holistic view of all the aspects of energy transition, setting a clear purpose, developing an agile strategy, and orchestrating the deployment of the full suite of solutions with the ability to adapt and leverage. It's a mouthful, but what it means is actually you have to consider all aspects of the problem. You need to have a clear goal, why you're doing it. You need to have a strategy that is flexible. And then you need to use all available solutions in the best possible way, and still make room for uncertainty so that you can switch direction when you need to. Okay, then the picture on the right I took a couple of years ago is from Duke Energy. Things have been nice and rosy so far until recently, and everything is going to go haywire. So so I'm saying that for utility like TNB, we need to innovate to survive. So that's it for me. Let me check, just make sure. Okay, before I go to questions, since I was mentioned that I'm a member of SEAGRAE, I have a special deal for you guys. SEAGRAE Malaysia is inviting academics to become members. So for students, there's no membership fees. Okay, and what you will get is access to a lot of SIGRE publication. I think you know SIGRE, right? It's based in France. It's worldwide. So and then it allows you to participate in technical. So please let me know if you want to register American member. Uh, um, if there is a way for you to tell me, can you tell me which one have I achieved today? Which of these phases? I don't have the set phase. That means I haven't. So kalau boleh lah, if there's a way. So I think I've got to pass it on back to the MC for the next session, right?
Yes.
So which the final slide in the island kat mana? You want it here or this is fine? Okay. So satu, I apologize, Haziq, for taking all of the time, including the
No, it's okay. So can we start the discussion right now?
Yeah, I'm ready. I told you to filter out the hard questions, right? Just give me the easy questions.
Okay, the first one is from Miss Sherry Chang Sadly. The question is it safe if we use nuclear energy for power generation?
Okay, my only answer is go to YouTube and you Google it because now you take two countries, France and Germany. Now, the world has changed. Okay, all this energy transition, it first started out, we have already had the technology for renewables. We built the solar, I think, years ago. Okay. But things that drove the use of the shift to energy transition, number satu was in 1970s, we had the oil crisis, right? And then that's when the Americans got scared about prices going up. So then they started looking into this energy transition, renewable energy. And then the next key thing that happened, there was a few more, but the next key thing happened was Fukushima. Well, there was the 3 Mile Island, there's Chernobyl, and then there's Fukushima, nuclear accidents, those three. And then Germany, what they did was actually they shut down all their plants that they wanted to move to renewables. So surprisingly, the cost of electricity in Germany is very, very high. Okay, because of that switch from nuclear to nuclear plants are expensive. They are expensive because we have to make them safe, primarily safe. Okay, and then we have to worry about how to dispose of the waste. But it is essentially non-polluting. It doesn't produce greenhouse gases. Okay, now France has got 70% of their energy in nuclear. Okay, and they have got they are happy with, they have got quite a significant RE portion on their generation as well. Okay, now there's two schools of thought, essentially saying that we should still maintain nuclear for base load and for peaking in a way. Okay, safety wise, if you check, some people say that there is less accidents in nuclear power plants than in renewable energy plants. Because it seems that a lot of people are falling off the wind turbines and stuff like that. So Google it, YouTube, and you can say is nuclear and renewable energy. There's a lot of discussion on it, quite informative. So I hope that answers your question. To me, if you ask me for my personal opinion, and which I will always volunteer without being asked, I'm okay with nuclear.
Okay, so the next question is, what is the role of clusters in sustainable energy development?
Cluster, COVID cluster.
I don't know. Yeah.
I'm sorry, I think you got me there. That's one of the hard questions I told you to filter out. Haziq. I'm sorry, I don't quite get what you mean by a cluster, so maybe you can email me and then I will try and answer because
Okay. Wait. Okay. Next question is from Mr. Adiputra. The question is, since Malaysia is targeting 31% renewable energy capacity, what is the renewable energy capacity that has been achieved by Malaysia so far, and what are the efforts made to continue raising to achieve its target?
uh, macam I cakap lah, by 2025 we have got some target, right? Currently I think we are about 6%. We've still got a long ways to go, but I caution you because how you calculate the renewable energy punya capacity, because some take large hydros as part of RE, okay, and some don't. So I really need to know when they say percent, I need to understand the base. But we still have a long way to go. Okay, we have got a lot of large scale solar projects coming on. I have to check, but I recommend that you go to two good sites. One is Single Buyer on your website. Okay, you type SB, single buyer, and then they've got lots of information, especially on generation capacity. The other one is you can go to the Grid System Operator, GSO, www.gso.org. So that is also another good place to get information. But I think I hazard to guess that 31%, we have got a long ways to go. Some people that I talk to think that our current system can only take up to 24% of RE. Okay, unless we do something drastic, which the one I'm putting forward, and we have to put in storage, everything under the grid flexibility solutions. If we don't do it like that, we can go up to maximum 20 to 24%. And then after that, we'll be walking on a thin ice because if we put too much, we might lose the whole system in terms of operations. My personal opinion, remember my disclaimer, you cannot take anything that I say. Basically, I won't be liable for whatever I say. I hope that answers the question.
Okay, thank you. The next question is from Mr. Wei Hon Yi. The question is, instead of tuning down conventional power plant during midday as mentioned in the duck curve, how about applying BESS where it has potential to mitigate the risk of over-generation at the Duck Valley? So is there any utility scale ESS project carried out by the government since Malaysia has started the projects of BESS in behind the meter service?
Yeah. Okay. You've got that. That is a very big question. Number one, you're talking about grid connected storage, and the BESS is actually battery energy storage system. So you're specifying on single type of storage. The other one that you mentioned is also about the behind the meter storage. That is also something. So I will address one by one. So in terms of the large scale storage, it is going to be a necessity. Okay, it's a must. But in what form? That is what we need to actually put more thought on. Storage is definitely required. Let me give you an example. there are many ways that you can you need to make money. You can deploy batteries as a source of energy or as a means to support the grid. Okay, so those are two services. Number one, you sell energy. The other one, you sell services. Now, in Australia, if I'm not mistaken, remember the blackout, and then Tesla came in and offered their batteries. They did it within 1 month. They installed 100 megawatts of batteries. Okay, there was their business model initially was actually every time it's a service. So every time they say they intervene to help the grid, that means every time the frequency goes down and the battery comes in, they should get paid. Okay. The funny thing that happened was that because batteries are so fast acting, okay, the nature of batteries is that once you have a once the um, once the frequency just drops, it will come in and support. The system response is almost instantaneous. That I think at the start, the business model doesn't work because the system never detected any interventions because it was so fast. So the nature of battery is this: it's fast acting, but the support that it provides is very time limited, the capacity. So traditionally, so that's why I say when you look at storage, you need to know, you need to design the intervention. You might want batteries or fast acting storage to support at the point of for frequency fluctuation. You need to have a slightly longer term storage, okay, so that you can allow the hydros to come in. If you've got gas turbines to come in, you need for them to start up. And then finally, you need to have a longer term storage because you need to do the things that you suggest. When you have a lot of renewable energy, you need to use that energy to charge your batteries, to fill your storage. So you're on point there. That's why I'm saying there's a lot of opportunities. Now, going back to the second thing, which is household behind the meter service. It is, let me see, how do I put it? Battery in a home is small. Okay, you can probably provide yourself, but to support the grid on its own, it's very, very small on its own. But together, if you can manage to aggregate it, then you can provide a viable support. But that's the key word, aggregation. So there is an opportunity there as well. But one thing I found out is that when we were looking into this, our Malaysian houses are not designed to have space for batteries. So in fact, my wife always complained that I'm keeping too many things, so not enough space. So now you want to put in a battery, so it might be an issue. But then there's also opportunities. You can have community battery storage, community energy storage. There's also another opportunity. I hope I'm inspiring a lot of entrepreneurs. Okay, I hope I answered the question. Ada lagi tak? Any more? Remember only the easy ones.
The easiest one.
Tak ada. I'm just kidding. Aziz.
Okay, sorry. Next question is from Miss Angela Teo. The question is, as we know, dust is the biggest challenge for building solar farm in Malaysia. Is there any method to solve this problem?
Dust, D-U-S-T.
Yes, dust.
Oh, I think they are coming up with, I think there's new technology, right? The clear glass something that is supposed to be more impervious to dust collection and stuff like that. They're coming out with new materials. Large scale solar, the solar panels, the technology is still evolving. I think they're trying to, they're dealing with the issue of dust. They're coming out with materials that are not resistant, but can handle that issue. So again, my advice: Google. But I've come across them being something doing there's some research on it and some work on it in terms of materials they use.
The next question is from Sir Khaldun Ahmed Kaid. The question is, if we replace more than 50% of conventional generators with PV systems, so what is the affordable solution for the loss of inertia problem?
Okay. You can the large scale solars, the inverters, you have smart inverters. You can program it to simulate inertia. That means injecting VARs and then okay. So the other way is actually okay, couple solar with batteries, then you will actually have that support that is required. So that's my quick question. The grid, people who operate the grid are not too worried about large scale solar. Okay, because the grid code has put in provisions to cater for inertia, for fault, riding through faults and stuff like that, and supporting voltage. So as long as we make sure our grid code, when solar, large scale solar gets connected to the grid, has got that can provide that service, that capability, then we should be okay. The ones that we are worried about is the small household solar. Okay, because when a large scale solar company wants to hook up to the grid, they need to do system studies on what is their impact to the grid, and then they need to be able to mitigate it. For people who put up solar panels on their roof, no such thing as system study, right? Because number one, they cannot afford it. So they are, if household solar, rooftop solar picks up, it may be a point of concern if we do not control the type of inverters that they use. I hope that answered the question.
The last question is about the SIGRE registration you talked about just now.
Yes.
So how do we register SIGRE students membership for free? Can you show us?
Actually, this one, okay. I think the easiest one is actually for if you want to become a SIGRE member, can you just email to me, and then when you put the title SIGRE student membership, and then the secretary will get back to you, because our website is down, I think. So the only way to register is actually for currently contact me. I hope that answers. My email is there.
Uh, Thank you. Okay, uh, thank you to our speaker for such a lively discussion and giving such a meaningful knowledge. In fact, we have once reached up to 139 number of participants. For participants, we hope that this seminar will benefit you in many ways. Thank you to the organizer for organizing this event. For your information, we will be having another 5 incoming webinars throughout this semester. The next one will take place on the 19th of May with the topic Energy Efficiency and Conservation in Malaysia. Stay tuned for more updates. With that, I wish you all a very good day and stay safe. Assalamualaikum and thank you.
Waalaikumsalam. And then thank you for everything. Thank you for having me here. I'm sorry if there's any shortcomings. I hope inspired some people. And thank you. Assalamualaikum.
Thank you, sir. Salam. So the end meeting ke?
Boleh masih lagi.